Buenos dias. I know I have a very difficult accent sometimes, and I'm very difficult to understand, so you'll be glad to know I've also written my slides very, very slowly. So I guess what I want to talk about is, and I'm just going to put that proposition out there, is should we genotype every single animal in each of our respective countries? And you may ask why, and that's essentially what I want to cover for the whole of my 30 minutes talk. But you also might ask how. And I am familiar enough with the Uruguayan traceability system, and it would be, I think, one of the best in the world, but also in Europe. If I would have said pre-BSC, so in 1995, if I would have said that every animal in Europe will have a unique identification number that sticks with it throughout its life, you probably would have said I'm crazy. Now, I am a little bit crazy, but of course we know that we do indeed have a unique identification system. And this is the tag system that we use in Ireland and in the rest of the EU. So what if we were to just add a little vial to the top of that, which we do in Ireland? We take an ear sample of every single calf, dairy and beef, born in the country. So there we have access to DNA of every single animal in the country. And what I want to talk about is what is the potential benefits that could be there from looking at the DNA or genotyping that individual. And here I've just given you a sample of what the potential benefits are, and I'm going to go through each of these individually. But you'll see when we talk about genomics or DNA, most people will think about genomic selection and more accurate EPDs. And that's what I have here. But that's only one component, and actually I'm not going to talk a lot about that because Dorian and Nacho and others are going to talk about that. I'm going to focus on predominantly the other benefits that are there from DNA technologies. In breeding, which I have in blue, but there's also from a production perspective, what I have in green. We can optimize our management systems based on the genomics or the DNA or the breeding values or the EPDs of these individual animals. And all of this is really based on having access to a large database of genotyped individuals. So if we just start with parentage assignment and traceability, if we take the two of them together, everybody here, we all have two strands of DNA. One we got from our father and one we got from our mother. And it's the same in cattle. And I will transfer half of my DNA to my sons and daughters, and my wife will transfer another half. So if we look at the bottom, we have this offspring. It has two strands of DNA. Now, we want to know, does that belong to the sire? We have the DNA of the sire on top. Because I just told you he transfers half his DNA, we can compare the DNA of the offspring to the sire. And we can see here that they match up. In fact, that sire would have transferred that half, the yellow half of his DNA. So yes, that is a good parentage match. If we take another example, and hopefully you can see here that this animal does not belong to that sire. The A's and the G here do not match up to an A or a T here with the both of them. So that sire is not the true sire of that individual. However, by having access to all the DNA of all the males in the country, or at the very least all the breeding males in the country, and this is what we're striving for in Ireland, is we can actually look at the entire database of all of these potential fathers, and we can identify who the true sire of that calf is. Of course, this requires all the animals to be genotyped so that we can actually scour that entire population. And if we look at commercial cattle in Ireland, our parentage errors are around 17%. So that's where the sire does not match up to the individual calf. But 60% of the time, so the vast majority of the time, we can actually tell the farmer, no, that is not the sire, but this is the sire. And we are 100% certain that this is the individual sire. So there's a huge potential there. From a traceability perspective, it's a lot more simpler. So we can look at a meat sample on the bottom. That is the DNA profile of a meat sample. It's just made up of A, C, T, and Gs. And you can see that that directly belongs to the individual animal. They're exactly the same match, 100% match. So that meat sample, the steak that you ate last night, we could potentially trace that back to what animal provided that individual steak. If we look at the other scenario, we can see that that meat sample is completely different to that animal. So therefore, that meat sample does not belong to that animal, or that steak does not belong to that animal. So we can get 100% traceability, but it's all based on having all the animals in the population genotyped that we can scour it against. So they're the first two. Next lot I'm going to look at is really helping you with mating advice. So looking at inbreeding, looking at major genes, myostatin, things like that, and also lethal recessive genes. So recessive genetic disorders, the bad news I have for you is that everybody here is probably carrying around 2 to 20 lethal mutations. And that's why it's a bad idea to mate with your first cousins and things like that, because the chances of those appearing are very, very high. But it's an important point. So traditionally what we would have said is if a bull was carrying a lethal mutation, we should cut its throat, get rid of it. But I'm telling you that if we do that, we will be killing everybody in this audience because we're all carrying them. So we need to look at monitoring and managing the mating of these animals as opposed to eradicating these lethal mutations in our population. And I'll just give you an example. And the example I'm using is from the dairy world because, of course, we all know that the heifer doesn't have any lethal mutations, but that's not true. But if we just look at the dairy world, we have two carriers. So the bull is C, or the cow is CA, so it's a heterozygous, a copy, carrying one copy, and the sire is exactly the same. Now, if they mate, we remember half the DNA from the sire is transmitted and half the DNA from the dam. So if the C from the dam and the C from the sire come together, it'll produce a double copy CC calf. If the A's come from the sire and the dam, it'll produce a double copy AA. And then, of course, you can have the C from the cow and the A from the bull, or vice versa. So you can have, again, an animal who's carrying the mutation. If it is what we call a recessive mutation, which is it really only appears when a double copy carrier, we will see that the CC animal, in the case of CVM, which is a dairy lethal mutation, that animal will die. The vast majority of cases, it won't even appear as a calf. It'll die in utero or in the embryonic stage. While on the right, the AA animal is not carrying the disease, but the CA animal, the one copy carrier, is still carrying the disease. It's not expressing it, and you don't know it is expressing, or it is carrying it until you look at its DNA. So as I said, the main benefit of this is it'll actually allow you to identify. You won't know, other than if the cow had several progeny and a lot of them had died, you might guess that it's carrying it, but you have to look at the DNA profile of that individual. So in reality, we have this animal, this cow, who is a known carrier. Okay? We have genotyped it as a known carrier, and it produces a bull calf. Now we know that there's probably a 50% chance that that bull is carrying that particular mutation. And we know if we sell that bull, we could make big money if it's not carrying it. But if it is carrying it, we could actually lose a lot of money. So therefore, if I was a breeder, I would probably say I won't look at its DNA. And then I'll sell this animal and I'll make big money, and in fact, it could be a carrier, which is bad. So again, why I'm saying is why we need to genotype all the animals in the country is that as breeders, you would have unequivocal access to that. So you would know in fact whether that animal is carrying any of these lethal mutations. And if we look at it again in the dairy world, there are 4 main lethal mutations that we have found in dairying, and we can see in Ireland, around 2% of animals are carrying these lethal mutations. So when they mate, there's a 25% chance that it will not result in a live calf on the ground. So it is one of the contributing factors to calf mortality and to infertility, or zero pregnancy rate amongst animals. And another thing, and this is something I show my PhD students, it kind of surprises them. Now, I don't want you to go away and try this at home, but essentially means that theoretically at least, you could be related to your brother or sister. You could mate to your brother or sister and result in no inbreeding. The chances of that happening are extremely, extremely unlikely, but I want to show you how it can actually happen. And here we have a bull and a cow. And as I said, every one of us carries 2 strands of DNA. So this bull, he has 2 pieces of green DNA, and the cow has 2 pieces of red DNA. Now, when they come together, they'll produce a calf. And of course, the bull will pass on half his DNA, so he'll pass on one green bar, and the cow will pass on one red bar. And the same thing happens on the other side with two completely unrelated individuals. So we have a bull and a heifer calf. When they mate to produce a bull calf, he got the red piece of DNA from his sire and the blue from his dam. And they mate again next year, produce a heifer calf this time. The heifer calf received the green from its sire and the yellow from its dam. Those of you that are quick will see that those two calves, they are full sibs, so they have exactly the same sire and dam. They are completely unrelated. They can mate and result in no inbreeding. And there is no way you can know that without looking at their DNA. Those of you that had had the extra cup of coffee this morning will realize, in fact, that that bull, the bull calf, is completely unrelated to its grandfather. And similarly on this side, this cow is also completely unrelated to her grandmother. So again, we can start looking at relationships or mating of not so distant relatives. So managing inbreeding. And the only way we can do that is through genomics. And this is just to give you a real-life example. This is from the Limousin breed in Ireland. What I'm showing you here is the pedigree relationships on the bottom axis and the relationships based on DNA on the vertical axis. So if we take here, these would be, they're sharing 25% of their DNA based on pedigree. These are half-sibs, or they could be more distant relationships. If we look at their genomic relationships, we can see some of them share 35% of their DNA, while others share none of their DNA. Now, some of this could also be due to pedigree errors. But what it's showing you is that animals that we thought were based on pedigree were extremely related were not actually related at all. So they could be mated and result in no inbreeding. And then, of course, we have the pedigree gaps, where pedigree is missing. So if you have two animals and you don't know their sire or their dam, to you they're unrelated because you don't know who their sire or their dam is. So they get a relationships of 0, while in fact the genomics is telling us that some of them are actually share 50% of their DNA, so they should not be mated or they will result in strong inbreeding. Again, to do something like this, you do need all the animals to be genotyped. The next one, moving on, is breed composition. And what you can do, or Hereford is a very good example, Angus is another example, where it's traded internationally as a superior product. You know, you go to the supermarket or you go to the restaurant or McDonald's and they're selling the Hereford steak, etc. But do we actually know for certainty every single animal how much Hereford or how much Angus is actually in those animals? So what you can do, and this is a real-life example from Ireland, from different breeds, is you can give the computer all the DNA and you can say, right, look for patterns and break up the population into individual patterns. And this is what it does. It breaks, say, 200 or 300 animals into a big group together, so they have a certain DNA profile. And then all the other groups, it breaks them up together. So it says this group here has a very different profile to this group, who have a very different profile to this group. You tell it nothing about the breeds. But when you color it afterwards based on breed, what it shows, quite clearly shows, is that the computer broke up the DNA profiles or the genotype based on breeds. It said that there's a similarity or a pattern in the Angus up at the top that is very, very different to something else. And similarly with the Hereford, there's a pattern in its DNA that is very, very different to the pattern in a Charolais or a Simmental. So if you have a steak, what you can do is look at the DNA and see where does that pattern fit. And in this example, the steak, the pattern fits within the Hereford. So that steak came from a Hereford animal. But in Ireland, which is more traditional as dairy crosses with the dairy, or crossing with the dairy and the Hereford, is you can see that this sample fitted somewhere between the Holstein and the Hereford. So that's the first cross, Holstein-Hereford. So we could go to the factories, or we could go to the retailers, or to the restaurants and say, we can guarantee to you that that is 50% Hereford, or that is 30% Angus, or whatever other breed we want. But then there's another example. We obviously need to be very, very careful about data confidentiality when they're talking about animals in Ireland. But if you have a Hereford bull mated to a Holstein Friesian cow, and assuming that they are purebred parents, that calf will be 50% Hereford and 50% Holstein Friesian. Yeah? Guaranteed. Now, if you were to use a Charolais bull, what is the breed composition of that calf? No matter what answer you give me, you're wrong. Because you can't know. You probably would have thought that the animal is 50% Charolais, 25% Holstein Friesian, and 25% Hereford. And that's what we all would have thought. And that's what we assume in our genetic evaluations. But in fact, that animal could have no Hereford in it. It could also have no Holstein Friesian in it. And you don't know that, or you can't know that, without looking at the DNA profile. So just mating a first cross animal to a purebred, you cannot know with certainty the actual breed composition of that calf. The last one on the breeding side then is, and this is touching on what Dorian and others are going to speak about, is increasing the accuracy of genetic evaluations. So what we do with genomic evaluations, or what we do with traditional breeding, is we have a bull and a cow, and when they mate, they produce a calf. Now, the calf, as I said, only gets half its DNA from the bull, and it gets half its DNA from the cow. So you're just looking at half of the genetic potential of the bull, right? And let's say that calf grows up and produces a carcass of 320 kilograms. So the reliability or the accuracy will be around 55% of that individual. Because firstly, we know that the environment has a large influence on carcass, but also we're only looking at a snapshot of half the DNA of the individual sire. But what if that sire produces lots of progeny? So all those progeny get a random half of the DNA of the bull. But because there's lots of them, and they each get a random half, what we have is the full DNA of the bull being expressed in the calves. So now if the bull has 100 progeny, more of its DNA is expressed, and the bull reliability for the carcass traits is 80%, or the accuracy is 90%. Because what we're doing is we're really just looking at the DNA of the sire via the performance of its calves, because we know it inherited its DNA. Now, what we want to do in genomics, and before anybody makes a smart comment, that's not me, what we're doing is we have this newborn calf. It's only 2 or 3 weeks of age, hasn't even reached puberty, it's just dreaming of becoming a bull. But rather than waiting for its DNA to be expressed in its calves, we look directly into its DNA. And that essentially is what genomics or genomic selection is all about. If we look at it in dairying in Ireland, we're getting reliabilities of around 60%, so accuracies of around 0.75. That's the equivalent of 45 daughters milking. How is it going in Ireland? This is just showing you the uptake of genomic evaluations from bulls in Ireland. So what we can see is when we launched genomic selection in Ireland for dairying in 2009, 1/3 of the semen sold that year, the dairy semen, was to this technology. Last year, 70%, so more than 2/3 of the semen sold in Ireland last year was to this genomic technologies. Because we've been doing this for so many years, we can look back and see what did we say this bull was back in 2009, and what is it today with hundreds and thousands of daughters. And what we can see is this genomic technology for us in Ireland is up to 23% more accurate than the older system. So it's not 100% accurate, and we never said it would be 100% accurate, but it is considerably more accurate than just using the parentage. However, size does matter when it comes to genomic evaluations, and we do need very large populations in order to estimate what is the best DNA profile for each of the individual traits for Ireland and for other traits. And what we see here is that how the reliability of genetic evaluations or the genomic evaluations change as our population size increases. So what you can see here is you really need around 30,000 individuals genotyped to get pretty good accuracies for moderate heritability traits. And in dairying, we could achieve this using artificial insemination, but in beef, we had to look at another route. And I think Larry Feeney talked a bit about this yesterday. We have launched what we call the Irish Beef Genomics Scheme, whereby our ambition to some extent is to genotype every single beef animal in the country, no matter what the breed is, with the view of trying to get the last graft to get to far right as possible to have more accurate genomic evaluations. So in 2014, farmers were financially incentivized to genotype 15% of their cows. plus all the natural mating animals, all natural mating bulls, so we could assign parentage a lot better. In 2015, last year, farmers were again financially incentivized to genotype over 350,000 cows, or females. So at the moment, we have over 400,000 genotypes, and just for interest for the audience, there's over 21,000 of those are Herefords. The platform that we use, it's not really that important. We built our own genotype platform. We genotype, at the moment in Europe, we genotype across many labs. It gives us a good flexibility to move different genotyping labs, to negotiate a better price. In Ireland, we will do 54,000 of these DNA markers for €22, all included. So that includes the cost of acquiring the ear sample, the cost of postage, the cost of doing the genotyping, and the cost of the genomic evaluation for €22. The accuracy we're achieving then, and I'm just going to show you some of the accuracies, and this is accuracy now, not at the BIF scale, unfortunately, at the normal accuracy scale. I'm just giving you a list of traits from the beef evaluation. This is the traditional accuracy we would have for those bulls, or those animals. They're newborn calves. So for calving difficulty, direct calving difficulty, they would have an accuracy of 0.6. The genomics is bringing them up to an accuracy of 0.72. What you can see is it's not a huge lift. So the equivalent progeny this would be the equivalent of this calf having 22 progeny. So it's a newborn calf, 2 or 3 weeks of age, and it's the equivalent of a bull with 22 progeny. There's not a huge benefit for some of these traits, the traits which we call are higher heritable, things like carcass traits, etc. Because you know yourself, when you look at a bull and you go out the yard and you look at individual bulls, the muscular bulls, they're probably genetically pretty good for muscle. So you really don't need that much of a DNA test to tell you that. You can judge it very well by your eye. So there's not a huge benefit. But would you know if they're good for fertility? You wouldn't really. It'd be hard to look at a bull and see is it good for fertility or age at first calving or survival. And you can see here that these are the accuracies we traditionally would get in Ireland for newborn calves, and we see this is the lift we get for using genomics. So it's the equivalent of this newborn calf having 100 daughters for fertility or 100 daughters for survival. A huge benefit of this DNA technology. So that's all the genomics. Now, for the last 5 minutes, I just want to finish off with how we can use this technology to help us manage these animals better. Okay? So which animal here is going to get BRD, respiratory disease? I'm not very good at cattle, but I know which one's going to get it. The one on your left obviously already has it. But traditionally what you would use is you'd have to take a blood sample, or any disease you'd have to look. Now, which one of these calves is going to get diseased? You don't know. But what if we could look at the DNA? And traditionally what we would have done is we would have looked at parentage. And if the parents said that, if the parents themselves got sick, we would have said, oh, there's a bit of a likelihood there that the calf might get sick. But now we could actually use genomic technologies to help us predict that better. And you might think I'm crazy. Again, I am crazy. But if we look at the human world, and there are 2 genes, BRCA1 and BRCA2, which some people have probably heard about. If you have the bad mutations for those genes, you have a 5 times greater risk of getting breast cancer and a 10 to a 30 times greater risk of getting ovarian cancer. So this technology could help us identify animals who are at greater risk of different diseases. And you might say, so what? Like, what good is it going to be? But you can actually do things differently. You can manage them differently. So if you have a group of animals who are likely to get a respiratory disease, you might put those animals into a shed or a house that had better ventilation. You might observe them a bit better for coughing, right? Or you could treat them. You could treat them and you could vaccinate those particular group of animals, or you could alter their diet or give them a better diet with better mineral or vitamin supplementation to increase their immunity against these individual diseases. I'll just give you this example. So big farmers, we all have individual sheds, and maybe we should be segregating our animals based on their genetic predisposition to individual diseases. So if we look at, for example, the group on the right here, we could have them genotyped at birth, and the genotype or the DNA could tell us that these animals are more susceptible to virus A. So we put all of those animals into an individual shed, but we keep them away from everybody else. And then on the other side, we have a different bacterial infection. These animals are more susceptible to an individual bacterial infection. So we put them in another shed and we vaccinate them. And then we keep all the safe animals, or the animals who are less susceptible to disease, in a different shed. And of course, if you imagine things, you could do this also for growth rate. So traditionally, in a multi-breed population like we would have in Ireland, we would probably group all of our Charolais in one pen, all of our Belgian Blues in another pen, all of our Angus in another pen, and maybe the odd Hereford. But what looking at the DNA will allow us to do, it'll allow us to put the fast-growing Herefords in with the Charolais and manage them accordingly, because they're at the extreme of the distribution. And there is a huge potential to do this. And without going into this slide in much detail, what it shows is the accuracy that we can achieve for different prevalence of diseases and for different heritabilities. So if we take, for example, tuberculosis. So tuberculosis has a heritability, TB, of around 0.15, and it has a very low prevalence. So that means that we could get an accuracy, be able to predict whether an animal will succumb to tuberculosis if it's exposed to the pathogen. We'd be able to tell you that with an accuracy of around 75%. That's what this is telling us. And I did it. So I did a genetic evaluation for tuberculosis for animals as newborn calves, and I followed them throughout their lives. So if I looked at the bulls that I said, just based on parentage, that these were the worst 10 genetics for TB, and then I have the group of animals, and there were several thousands of animals in this, who are the best, so they're less susceptible to TB. I followed them throughout their lives. The ones that I said were the worst genetically, 31% of them got TB. The ones I said were the best genetically, 5% of them got TB. So there's a phenomenal potential that we haven't tapped into enough in being able to segregate animals based on susceptibility to individual diseases. So just to conclude, I didn't go into it in great detail, but if we look across the world, with the exception of really just one country, genomic selection clearly works in dairying. I showed you that 70% of the dairy semen sold last year in Ireland was from genomic bulls, and that's pretty similar across the world. We're also seeing across the world, when we look back, farmers are no fools, you know, and you know this yourselves, is they are using the technology which they know works. And this technology clearly does work. However, hopefully what you got from my talk is that although when we talk about genomics, most people probably think about what Dorian and Nacho is going to talk about, genomic evaluations and improving the accuracy of genomic evaluations and EPDs. But hopefully I've showed you that that's only really a tiny bit of the potential that's actually there. There is so much more information that we can get from DNA that will allow us to breed our animals better, to decide which ones are least related, and manage lethal recessive mutations, but also manage our animals differently, segregate them differently based on their genomic potential. Cleaning up the pedigree. And this becomes really, really important, and being in Uruguay, of course, it's really important, being a large exporter of beef. Imagine going to the high-value markets, going to the Russian market with the traceability system that is in the EU and in Uruguay, and being able to say, not only will we tell you who that animal is that carcass came from, we'll tell you every single farm that animal has been to. But not only that, we'll tell you who the father has been through, and we'll tell you who the mother is, and we'll tell you every single farm she's been through, and potentially even her mother. So there's a huge potential, I think, to drive into the higher value markets by using this genomic technologies. Thank you very much.